Good afternoon, everyone. Prynawn da, pawb. Bit worrying that everyone got up and left. I'm not that bad, honest. Well, time will tell. Okay, I want to talk about power consumption now in optical metro transport networks. So rather than focus on how many nuclear power stations you need, I'm not going to do that. I'm going to focus very much now on the metro access part of your network. I have to give you a warning up front in that there's the saying of lies, damned lies, and marketing statistics. The figures quoted here are to make you think. They are not absolute figures. I'm here just to try and make you think a little bit about how you're using your power in your optical networks in the metro access part of the network. So don't click the hyperlink. Oh no, sorry, you can click on the hyperlinks here. These are some studies which build upon the brilliant presentation by Jeff this morning, which talks about how much power is used in telco networks. And the lies, damned lies, and PowerPoint slides again. You know, between 20 and 40% of power is used in the telecoms network. One thing we do know for certain, above death and taxes, is power will get more expensive. So power will become, or if it isn't already, a much bigger part of a telco's, a service provider's costs. Some large operators, I'm not going to talk about the hyperscalers because that's a whole different level. We're also seeing pressure from regulators. It was mentioned again in Jeff's presentation about the CO2 emissions and how you can become more CSR responsible, because everyone wants to become more CSR compliant and responsible and hit those targets, right? So focus on the metro. I'm not going to do long haul stuff. I'm not going to do thousands of kilometers. I'm very much focused on a level 1, so I'm basically a plumbing guy. It's all about optical networks, the plumbing stuff, right? So its metro network is it's maybe to a small data center, to a customer site. It can be ring or point-to-point. It can be carrying Ethernet, CPRI, eCPRI, fiber channel. Does anyone still use that? Data rates, I'm looking at 1 gig to 400 gig. I realize the 800 gigs and terabit stuff is coming, but the figures that the data behind all of this is up to 400 gig. So we could be talking about backhauling of residential services. We could be talking about mid-haul, front haul, or backhaul in a mobile world. But there are 2 ways of doing it at transport level. You can do it via passive transport or active transport. So just a couple of scenarios. So this is, if you like, your traditional. When people think about WDM networks, even today, they think about a transponding-based solution. And on the left-hand side, you have your switch or router, or router as the proper words. On the left-hand side, you have some gray optics, 850, 1310 cheap optics, into an active system. It goes through a muxponder, a transponder, and it goes out on all those nice colors. And then there's some filter, there's some filter that's at the end that pulls all them together and sends it out over your fiber optic cable, single fiber pair. So that's what most people think about when they talk about a WDM system. We've evolved. Now we have things called transponders, and this means on the left-hand side you still got your gray optics, patch panel into the gray optics, but now you're combining them onto a muxponder, again sending everything out over a single lambda, a single frequency, a single color. And again, there's perfectly good reasons why you want to do this. And then we got this wonderful thing that everyone's getting excited about, which is called IP over DWDM. IP over DWDM is nothing new. We've been doing it for 20 plus years. The only difference is now, because we're doing it at 400 gig, it's all exciting IP over DWDM. It's nothing more than a color transceiver in your switch router going through a filter, shoving it across the network. The transceiver determines the speed and the distance, not the mux. We were doing this 20-odd years ago, but it was 1 gig stuff then. Now it's like 400 gig and 800 gig. Sorry, things are flashing around me. It's not me, is it? No, it's me. It's not me. Good. So IP over DWDM, 100 gig, 400 gig stuff, away you go. Great. So now, just a bit of background about what we're going to go into. I'm going to go into some slides in a minute. Just want to position that as we go into those slides, okay? So again, I'll reiterate, we'll go in short haul. We say 80 kilometers. In Europe, it's typically 40 kilometers. In the mobile world, it's 15 kilometers because of the latency issues associated with that. So we're talking about the metro access. I called it last mile once, and I got told off that it's not last mile because it could be more than a mile. But anyway, it's the access bit, the expensive bit for you guys, the bit getting it to the customers, because they're always expensive. I'm not looking at layer 2, layer 3 and above. This is basic. This is layer 1. I'm not including amplifiers because if you use an amplifier, you need an amplifier anyway, and that's going to add power because you need to power it with something. I'm looking at comparing it at 1 gig, 10 gig, 25 gig, 100 gig, and 400 gig. I would say normalized per link. So what we're saying here is that it's one point, it's a service at point A to a service at point B. You can do things like mux bonding, and it's becoming very prevalent today. We're perhaps taking 100 gig in, mux bonding it into a 400 gig out. It gets very complicated measuring the power usage in that sort of scenario. So just going back to this slide slightly. So on the left-hand side, you have the passive transport. You sure it's not me? It's a cable. So on the left-hand side, you have the grey optics at the top, so that's point-to-point, so you can see that on the right-hand side, the little schematic. Then you have your passive WDM, so you've got colored transceivers at either end. So we're looking at a service, per service, okay? And then we've got the transponding bit, which is some grey optics, some on the customer side, and then some colored optics on the line side, and the mux bonding one. On both of the active systems, you've got power supplies. You've got more transceivers. You've got management cards. They all take power. They all take power. So let's look at some transceivers. Everyone's aware of transceivers. This is a 1 gig transceiver. And between 1 and 25 gig, there's very little difference. It's not dependent upon, data rate doesn't increase the power per se. Yes, there are some small differences between 1 watt to maybe like 1.8 watt. But there's not massive difference. What does make a difference is if you use standard temperature transceivers versus extended temperature transceivers. That can have an impact. And the reason for that is that some of the colored WDM transceivers have temperature controllers built into it. So you can buy some really, really cheap transceivers at a 1 gig, but they won't necessarily have temperature controls, which could work nicely in a data center environment, but won't necessarily work very well if you're in a street cabinet somewhere in Las Vegas or some other place where it gets very hot. The transceivers from the manufacturer's point of view are more or less the same. Yes, there are some slight differences, but they're negligible. They're negligible overall. So they're just looking at some 1, 10, and 25 gig transceivers. And then we're looking at industrial temperature, and that might have an effect. I know you probably can't see it, but at the bottom of the graph there's 2,000 and something transceivers being tested, okay? 97% of the transceivers, this is based on a 1 gig SFP, LX, pretty common transceiver, 10 kilometer. 97% of those transceivers consume 50% less than the datasheet states. 50% less than your datasheet states. Easy for me to say. So if the majority of your transceivers use less power than the maximum stated in the in the data sheet, how do you plan for those access nodes? How do you plan for those street cabinets? How do you plan for that stuff that's getting up closer? Are you planning for the maximum, or are you planning for what's available? Within a data center, this is all measured, right? You know exactly what's going on in a data center. But as you get further out, closer to the customer, it all gets harder. As I said at the beginning, this is to just make you think about a few things. I'm not saying what the right answer is. Okay, just moving on now. In the various colors, and apologies to people who are colorblind, we had to use something. So on the yellow one at the top is the data sheet. So at the bottom, we have various transceivers from 1 gig to 10 gig, various reaches, etc. So the data sheet is the yellow one. So that's what it says in the data sheet. The orange one at the bottom, we've assumed that its ambient temperature is 25 degrees centigrade, which is reasonable. Uses less power. You start using more power if it gets very hot or it gets very cold. But it's always a fraction, a small percentage, of the stated power in a data sheet. Right. When we start getting to 100 gig and 400 gig, it gets more complicated. And it gets even more complicated under gig. And anyway, COWI is important because you can have, in the red there we've shown two 100 gig coherent transceivers. One is 6 watts, the other is 23.6 watts. Depends upon the electrical lanes. So the COWI determines the electrical lanes. If you've got 4 electrical lanes or 1 electrical lane, or even 8 electrical lanes in some transceivers, that will have a big effect on the overall power usage used in a transceiver. They vary vastly differently from manufacturer to manufacturer. So the table there just gives you some examples. But direct detect versus coherent makes a big difference. In a simple direct detect transceiver, it's pretty simple. You have a photodiode, you have an in and an out, and away it goes. With a coherent transceiver, you have a DSP built in. You have some hybrid couplers and a few other bits and pieces. Something has to power those DSPs. Therefore, your power usage goes up. Okay? So, just summary on the transceiver point of view. The datasheets state the maximum power consumption, but it can vary hugely to what's actually used. We've looked at a model based on typical power consumption, and we've assumed our models around 25 degrees ambient temperature. So direct detect, we've assumed 57% in the model. I've got a couple of slides coming up in a minute. We'll explain all this. So we've assumed 57% is the approximate power in a direct detect, and 87% in a coherent transceiver, dependent upon the specific design of the DSP within the transceiver. Can I take questions at the end? Is that all right? We'll come back to that if you like. I'll lose my train of thought otherwise. And I've lost it. Right, power consumption. So what we've done here is we've taken our active WDM system, and one of the things is that if you have an active system, you've got a power supply, you've got a management card, you've probably got redundant power. Most of the time, they're not fully populated. Therefore, your actual power per service is probably higher than it needs to be because you're not fully populating it from day one, typically. So if you have a 3RU chassis with 2 line cards for 1 service, the power usage overall is going to be much higher than if that was a fully populated 3RU chassis. That's what we're trying to say there. We've been conservative with these figures, and what we're saying is that the most active systems tend to use more power than we've assumed in our typical model. I've got to mention cooling, air conditioning. It's very difficult to actually work out what cooling and air conditioning would do to the overall power, But again, what we've done in terms of the model is assumed that if you've got 1 watt of power that you're using for a transceiver and everything else, you're using an additional watt for air conditioning. And we've applied that versus an active or a passive transport system. So basically, if you've got cooling, you double everything. Simple maths. I like that sort of maths. I can manage that. Okay. So getting into the nitty-gritty. So at the bottom, on the left-hand side, we've got 1 gig, 10 gig, 25 gig, 100 gig, 400 gig. In the gray is a point-to-point gray transceiver. And you can get 120 kilometer 1 gig transceivers, right? So they can still reach a reasonable distance. The orange color is using passive WDM. The yellow color is using a transponding solution, an active transponding solution. And the blue color is using a muxponding solution. And as you can see, no surprise, quell surprise, the faster the data rate, and the more of it, you use more power. No surprise there, right? There's a little green dotted line through the middle. This is where we switch from direct detect to a coherent transceiver. Direct detect, very simple, no DSP. As soon as we start going to the coherent world, where there's DSPs built, the power consumption increases significantly. That's what that line, that dotted line is showing there. So we can take an example. If I take a 10 gig WDM system with the transceivers because there's no power in a passive system, uses about 2 watts. If it uses about 7 watts on a transponding solution, 19 watts on a muxponding solution. As you can see, the power increases significantly as soon as you go to the other side of the line, where we're starting into the coherent transceiver world. So a 10 watt coherent with an optimized DSP. Again, we've got optimized DSP because there's lots of different DSP types out there. So I'm trying to sort of stay both sides of this argument. Direct detect, 6 watts, and then you can go up to 41 watts and 128 watts. So rule of thumb is a transponding solution uses, damned lies, yeah, I mentioned that one. Transponding solution uses 4 to 5 times more power than a passive WDM system. A muxponding uses 10 to 20 times the power of a passive WDM system. This is all about, when I say passive WDM system, this is all this new IP over DWDM world, okay? If we add cooling to the figures, because I said we use simple formula, we've doubled everything. So the difference between this slide and the last slide is simply we've doubled the amount of power that's probably being used. Right. So this slide is really looking at what happens over time and how you add more and more services to this. This is the figures without external cooling. The use of industrial temperature transceivers can have an effect on these things. When an active power system is used, even when it's fully populated, it's not necessarily optimized it's not necessarily optimized to the best possible design, which will result in 2 to 3 times more power being used and increase, and I've got to be very careful with this last slide. I've used this last bullet point, can increase your necessary power consumption by a factor of 100. And it's great in terms of getting a response from people. So if you want to, if I want to use that for, if I spam you on LinkedIn, it'll be go, wow, 100 times, up to 100 times more. Let's be careful with these figures, all right? It's significantly higher. It is significantly higher. So I'm a bit ahead of time, but in summary, the continued use of, we're using more data, right? Everyone is using more data. Even in saturated markets, such as the Nordics, where mobile penetration rates are so high. What we're seeing is there's a shift now, not from coverage to basically still higher data rates. So people still want high data rates. They might be moving from a 5G, 6G, oh God, to a fixed environment. Certainly in Finland, we're seeing this, that mobile operators are seeing more and more people take up sort of fixed line services for their gaming and other stuff like that, because it still helps latency. Overall, data rates are still going up. We all know this. You can use up to 100 times more power than necessary. Transport networks can cut down this energy and your associated CO2 corporate social responsibility scope 3 requirements. Tick the box, guys. We don't say that you do not only use passive WDM. There are very good reasons why you want to use an active transport system. If you've got something on a remote site and it needs some management, you want to do some muxponding at a remote site and you want to be able to do some management as a demarcation device, the only way you can effectively do that is use an active system with management cards, so you can do loopbacks and reporting and everything else like that. If you own the equipment at the end site, then why not use passive? You can use a passive transport system and an active transport system in the same network, on the same link. They're lambdas, folks. I think I presented previously at other places. It's a lambda. Every single optical vendor in the world uses the same ITU, DWDM lambdas. C-band typically, there is L-band, we're not going to go into that. So there are 40, typically 80 channels specified in the ITU. Every single vendor uses the same lambdas, so you can use a passive system at one end and an active system at the other end. You can use an active to active, you can use a passive to passive. It's up to you. If I cite BT, for example, when they're building out their 5G network, the remote site at their cell sites, they're using an active WDM system because they've got so many radios they have to maintain, right? And they've got so much stuff, they can't swap it all out in one go. At the central office, at the BBU hotel, they're using a passive WDM system where they can get really, really high density. Density is an issue, right? You want to use as little space as possible. Why do you need, you've got engineers there, why do you need an active system at that location? Nobody can explain to me why you need an active system at that central office. Yet, the vast majority of networks are still being built that way. There's my contact details. Thank you, Joanna, for adding them at the last minute, because I forgot. I'd encourage you to, if you can, I know, hyperlink again, right? Shh, don't mention security. Every week we put out a 3 to 5 minute video about some aspect of optical networking. It's never a product pitch. The last one was about difference between UPC and LPC and APC connectors. I'm an expert on those things, you can tell. Encourage you to follow that. Follow me on LinkedIn. Invite me on LinkedIn. I promise not to spam you too much. Anyone got any questions?
We have time for a question or two. We've got one over Menti, actually. We'll start with this one over here.
So it's actually two questions. Let's combine them into one. Does cooling reduce transmission errors, or is it the opposite? And how does it affect the device's lifetime?
Yeah, okay. So if you run a transceiver over temperature over time, yes, it will affect the operation of eventually something will fail. Typically you start seeing bit error rates, failures, and eventually the unit will fail. So yes, you want to run it at the optimal temperature, but most of them will be able to manage some small variances. What was the first part of the question again, sorry? It was about...
does it reduce transmission errors, or do we see the opposite effect?
Okay. So if your site is going to have a problem, then just use industrial temperature transceivers. So basically then they can extended range from 0 to 80 degrees on some of the extended temperature transceivers. Unfortunately, not all transceiver types have extended temperature ranges.
Do we have a question at the front? Can you wait for the microphone? And
you have something direct detect or something? So is it something similar to direct attach cable or?
No. No. So direct detect, this is trying to show two transceiver types. Sorry, I didn't explain this very well. So at the top there is the direct detect transceiver, and it's a very simple transceiver. This is typically your 1 gig, 10 gig, 25 gig transceiver. Will be very simple in terms of what's actually inside it. It'll have a photo detector, it'll have an in and out, and it's very simple. As soon as you start going to a coherent, which is typically a single lambda, some of the direct detects, sorry, some direct detect can be a 4-channel direct detect as well, but they are typically cheaper lasers, much cheaper transceiver overall. As soon as you start adding a DSP in there, not only does the power increase, but also the functionality and the capabilities of the transceiver increase also, which is why you can get a 400 gig ZR transceiver that can go 80 to 120 kilometers. Okay? In theory, there is a 100 gig transceiver available that'll do similar as well, but that's the ZR, and that's all to do with the DSP processing that's in there, which also helps in terms of the modulation used for the additional reaches. Did I answer your question? In terms of direct detect cables, that's a totally different discussion.
We have a question here, and then we might have to do some maintenance on the screen. So this is the last question.
Given that the power numbers are relatively small, but the cost of optics relative to a kilowatt hour of electrics is quite high, is there a point where it's just not worth worrying about replacing more energy consuming units with more energy efficient ones, because the return on investment is just longer than the life of the optics?
Politicians answer yes and no. If you're in a data center and you've got hands in the data center all times, yeah, plug it out, plug another one in. What the hell? If the remote site is 40 meters up a tower on top of a hill in northern Sweden, the cost of replacing that is huge. So it depends. All of my answers come back to it depends.
Thank you.
Okay. That screen is not looking perfect. So if there are no more questions for Steve, then please join me thanking Steve for a great presentation. Thank you very much.